Good afternoon. Hi. I want to talk about today about how long-running services reduce the complexity. Also, probably in your architecture. My name is Ben Drücker. I'm co-founder and developer advocate of Camunda. We're basically an open source workflow automation company based in Germany. I've written that book. I probably mentioned that later on a bit. And if you want to reach out to me, there's my email address, there's my Twitter handle. I'm here till basically the early evening, so if you have any questions afterwards, we will probably run short in time in the talk. But approach me on Twitter, send me an email, approach me afterwards, ask me anything you like. That's it as a very short introduction. So there are a lot of things currently going on, basically in modern architectures with most architectures quite distributed ones. So hands up probably who has not any single remote invocation in his system at all. No RESTful, no SOAP, nothing. Oh, there's one. That's an interesting use case. So probably something embedded, or how does that work? No, that's interesting indeed. But normally, like it's everybody has at least one thing in his architecture, and that makes most of the systems a distributed one. And I actually like this metaphor very much for distributed systems. So the nice little hut over there, that's your service, your Java application probably. There you're on one JVM, you have a transaction management. It's nice and cozy, you have a heating, and it's great life to be there. So it's fun to develop within that hut. But whenever you open the door, you're facing the network and you're facing quite a lot of challenges with swallowed messages, turned around packages and whatever. So you have no idea what's going on out there. And that's quite a complexity to handle. I recently have published an article about that. Basically, I named it the 3 common pitfalls of microservices integration. It could be any distributed system, but microservices is the most catchy title at the moment, and how to avoid them. So you probably want to look that up. So a couple of the examples I do today are in that article as well. And they're an awful big pile of basically probable pitfalls in microservices. But I picked these threes, which is communication is complex, so it's hard to communicate within distributed systems. You might want to do that asynchronous, which is even harder sometimes not. I will briefly go into that later on. And basically my favorite topic is about distributed transactions. And I want to talk about that a bit today, and that's actually a great recursion of the talk itself. So I want to ask you for a bit of patience because of the title "Patience Pays Off." I come back to the patience a bit later on, but I want to lay some groundwork first. So let's assume you have any kind of system where you have a lot of services, might be these or many more, whatever. What we start to accept is that some parts of the system might fail. I mean, the bigger the system you have, the more services you orchestrate, and the more pieces of the puzzle you have, the higher the probability that something fails. And it's just, we start to accept that it's too expensive actually to avoid that, to make it such reliable services, such reliable hardware and whatever, and still then it might fail at some point in time. So we start to accept that. But the interesting part is that we want to avoid this basically taking down the whole system. So we don't want to get into these kind of cascading failures where the whole system blows up. So that's the basic idea of what we do. A lot of things we currently do in distributed systems are basically to scope these kind of resilience patterns and so on. I want to do a very simple example today, or want to start with a very simple example, and that's I basically just use 2 services for the moment. So I have a payment service, and that, because payment you very often don't deal yourself with credit card, you have an upstream credit card service you just call via REST API. So that's easy to imagine, right? I hope. Yes. Awesome. I used Java and Spring Boot in order to get going because I want to dive into the code as well. I don't want to have slides only. And let's quickly do that. So in the background, I have my Eclipse. There I have a bit of Java code. And actually, it's Spring Boot code. It's Java code, so it shouldn't be that hard to read what it does. And I don't want to go into all the details because that's simple Java and Spring Boot. So here I have a REST controller, I have a request mapping, so I map it to an API method to an URL basically. Whenever I do a put there, I want to retrieve a payment. Then I do some data stuff because I don't have real data in that example. And then I charge the credit card. And this is a bit of code using the REST template of Spring. You could do it in whatever way you want, where I create a charge request, send that to my REST endpoint with a post, get some response back, and that's it. So you probably have, who has done something like this in the past already? Okay, a couple of the people. So you know what I'm talking about. That's a simple REST call. So that's what you do naively when you start doing REST communication. What happens actually if I call that? It's very easy. So what I have here, this is the upstream Stripe service. From my Eclipse, I directly started the payment service. So what I can do, I can use a REST API in order to call the payment service, sending the put, and I get a response back, hopefully, yes. So that's pretty good. But very easy, I think. So let's see. So we get an HTTP, where is it? 200, okay. That's boring, I think. That's setting the scene. So that's very easy to get. So what happens, that's the next thing. I can now make my service responding slow. So now my Stripe service, the upstream credit card service, is very slow. It has a delay. What happens if I call it? That's a warm-up question. That's easy. It still works, yeah. What happens? It's slow. Yes, of course. So I do it again. What you can see is that it's blocking. It's blocking the request. It's blocking, it's blocking, it's blocking, until at some point in time, eventually I get a response. It still works, but it's very slow. And we're still in the warming up phase. And that's actually pretty bad, because why? Now the payment service is blocking, waiting for the upstream credit card service. And that means whenever the thread pool of the payment REST server is exhausted, we cannot handle any payment request anymore. So slow upstream services are actually inverse than non-working upstream REST services. So that's actually a pretty bad situation to be. That's actually well known. Who of you knows of the circuit breaker pattern? Most of you, that's great. Not all of you, so some of the people should do some homework, but most of you. There's actually a talk from Edson later on service mesh. That's probably good to go there. I'm not sure if he does it today, but he should also talk about circuit breaker. The beauty of the circuit breaker, and I used Hystrix to make it in code, is that it can be very easy. So here, and that's different to service mesh later on, but here I use a circuit breaker, and I basically just added this line of code to have a circuit breaker. And what it does now is whenever I do the post, it can, like in your house, when you have strange things with the electricity, it just switches off. And that means when I still having the slow service, but calling this V2 service, whenever I do that, the circuit breaker switches off. I get basically a Hystrix exception, so there was a timeout. But the good thing is I don't get down my payment service by this slow upstream service. So the circuit breaker is very important. And it was actually pretty good that most of the people know this. This is very common, actually. So the circuit breaker is very common. And this is what's normally called fail fast. So you want to fail as fast as possible to not, in this case, bring down all the thread pools of your of the different services, like cascading. But the important thing, and that's what I want to talk about today, is that this is not enough. Fail fast is not enough. So I want to give an example, and that's actually my favorite example. You probably have used an airplane before, yeah? You're kind of familiar with the concept. So you book a ticket, you go, you get an email later on when you book the ticket, and please check in for your flight. Your flight is ready for check-in. You go on the website, you select the seat, you basically confirm you don't have any dangerous goods, then you can book in. And the next thing you can do is there's a button where you can say, okay, now send me the boarding pass, right? So that's what you normally do. When I did that, actually last year when I prepared another talk, it was a great coincidence that I got an error message. In this case, I flew from Germany to London, so it's a German website, but I think you get the idea. They basically said, okay, there was an error sending you the boarding pass. Okay, so I got that error. What I imagined that happened in the background was something like, okay, they have that web user interface. They probably have a check-in component, a service, or whatever it is. And that probably needs some upstream services like output management to generate a PDF, or probably the barcode generation. That's doesn't have to be like this, but this is how it's in my head, actually, my own little word, it looks like that. And what I think that happened is that the barcode generation didn't work. And actually, I discussed it so often with customers during the last years that it seems that output management, PDF generation, is the greatest source of errors at all. Because if you mention output management in whatever meeting, it's always like, yeah, we have to do that. So I think this is pretty often the case. So the barcode generator probably didn't work. They had some kind of circuit breaker there because the website was still responding. That was good, which is not like the usual case. So that was a flight from New York with United. There, same button, I got this one. So that's really the worst thing you can do. The cool thing about giving this talk now a couple of times that I'm always happy if I see these kind of error messages because I collect them. And I have a lot of airlines by now. And I start to see patterns which use these kind of error handling or not. So this was United. So they even didn't have a circuit breaker. Everything was basically broken down. But it's still bad. Even if they have the circuit breaker, it's still bad because what do they do with that error they have in the barcode generator? They basically transport it to me as a user. Now it's my problem. I have to do something with it. What would you do? I ask that actually very often. And I have three common answers. So the first, it's kind of the end user answer. That's also what my mother could say. Something like, oh, I would print the page with the error message. Yes, that's great. I'm not sure if I get at the airport anywhere, but okay, I could print the page. The second answer is kind of the management kind of answer. Oh, I would escalate it. I would call the airline. Going on their nerves. Probably could work, would not work. What's the programmer answer? Very obvious. Try it off and on again. Exactly. Retry it. That's exactly what I did. I mean, for me as a programmer, it's even like natural. Oh, I retry it. Yes, of course. There's an error. I retry it. For my wife, that sounds a bit strange, but for me, it's normal. Okay, I retried it. It didn't work. I retried it like 5 minutes later. It didn't work. So I made me a calendar entry in order to retry it 4 hours later or 5 hours later. So I got reminded, I did the retry, it did work, so that I could resolve it. But I had to do it on my own. It was my problem. I had to do what I call a stateful retry because I had to remember it. I had to remind myself. I had to do it like a couple of hours later. And that's a bad situation, actually. The funniest part of this story is when I flew back from London, I flew EasyJet. And they even give me that work instruction, what I should do. They say, please log on again. That's the retry. If that doesn't work, please try again in 5 minutes. Oh, increase the interval. And the best thing is the last one. We do actively monitor our site. We'll be working to resolve the issue. There's no need to call. It's your problem. Don't bother us. Don't bother us. Solve it yourself. Okay, it would be much better if they say something like, okay, we have a technical problem. It's our problem, so we care about it ourselves. And we send you the boarding pass as soon as we can. Yeah. You're safe, we send it early enough for your flight, everything, it's okay. Because I don't have problems with the boarding pass not being sent right away. I need it when I go to the airport, not before. But I don't want to do the retry. So what they could have done, they could have done the retry itself, probably in the check-in component themselves. They have my email address, they have the mobile number, so they can do it without me at all. And that's one important lesson here, and that would even like reduce the scope which really has to see that failure message, who has to care about this failure message. And in this case, it's kind of customer facing. I see that from the outside. But you have the same problems if you have service-to-service communication within your whatever it is, service-oriented architecture, microservice architecture, distributed system. Whenever two services communicate, you have more or less the same problem. You can take the error and just throw it to the next service, or you can handle it. And handling it is very often the better user experience. And users are services. I also see them as kind of users. The problem, and that's actually why I see a lot of people not going down that route, not doing this, is now you have to handle state. I talked about that 4 hours to reset the boarding pass, for example. You have to care about that, because if you promise the user to send his boarding pass on time, you should do it, actually. It would be a really bad experience if you then don't do it. So you have to handle state. How do you do that? Normally, like the naive approach would be what I call a persistent thing. because I would say like a database table, but nowadays it could be like also a document, it could be persistent actor. There are multiple things you could do, but it's kind of your own persistent thing. And the problem with that is normally not persisting something. We're pretty good at that, more or less. But you have to do a lot of things additionally, because then you get these kind of scheduling, for example. You have to do that retrying. Oh, does the barcode generation now works? Does it now work? Does it now work? You have long-running things, because if you retry that for hours or even days, and you change the logic, you have a kind of versioning problem. What is with already running stuff, what to do with new versions and these kind of things. You have to operate that, so you probably want to see what's currently going on, which are the current active retries. If you fix the barcode generation, probably you want to trigger the retries, or you only want to have like one being retried to check if it's now working or whatever. So there are a lot of things you have to do, and that normally gets a lot of accidental complexity, and that's pretty true. I see that very often. There's a second approach, which is for me very natural, but I see for a lot of developers not. There are state machines out there. Most often they're named workflow engines, and they can handle these kind of things. The normal like concerns I hear when I propose this kind of solution is that they're very complex stuff. It's very proprietary. Like you buy from the big vendors like a huge suite. You have to deploy that on machines. It's very slow. It's kind of a low-code approach. So it's really hard for the developers to keep track. And it cannot handle the load we have and all these kind of things. And that's actually not true. And I want to quickly go through that. If we look at the current market of workflow engines, and that's actually pretty interesting. We see a lot of things going on, especially in the last 2 or 3 years. So there's, first of all, we had a serverless talk just before me in that room. So if you look at the serverless world, most of the vendors start having something there. For example, AWS has the so-called step function. So that's how you can basically make a workflow, a stateful workflow within the serverless world. So it's pretty relevant there. They launched it 1.5 years ago at the AWS reInvent. So it's pretty modern what they do there. At least from the marketing part of it. If you look at all the Silicon Valley companies, you also see that they do something. So if you look at, for example, at Netflix, they released Conductor like 2 and something years ago, where they also have kind of a workflow engine underneath. And Uber did more or less the same thing with Cadence. Both of them only live in the world of the of their company stack. Like Netflix, you need a Dynamite DB, which normally you don't operate, or Uber is only with Cassandra and Go, which kind of limits the use cases. And there's quite a big group, especially in the Java world, of what I would call lightweight open source engines. So like probably heard of Activity or JVPam or Camunda. The Camunda engine is the one I want to use for today's example. That's like coincidence, the one from the company I co-founded. So that's the one I know best. But the others are pretty comparable. If you wonder, we are currently also working on an open source project called CB. That's probably interesting because there we can scale up the workflow execution beyond what we know from these other kind of engines where you rely on a relational database, which kind of limits the scalability. But there we rely on append-only logs and achieve really truly horizontally scalable systems, but I don't want to go into details of that today. If you have any questions, let me know. What I mentioned earlier, I will go for Camunda for today. And in your head, you could replace it with the others. I'm pretty convinced that we are better, but do that exercise yourself. So it's not about Camunda as the best. It's about what I want you to remember is that there are these kind of lightweight engines available, and if you have these kind of problems, you should use that. So let's apply that for the use case we had in hand. So we have that post request, that simple REST call. And what I could do, and I actually also prepared that to save a bit of time. So we still have our REST controller. That doesn't have changed. But in this case, I said I'm using Spring Boot. So what we have in Camunda is a Spring Boot starter. So you just add a Spring Boot starter to your POM, and then the workflow engine is started as part of Spring, auto-wired with the data source, transaction management, all these kind of details. And then I can just use auto-wired to have the process engine there. The next thing is the next thing I do whenever I start it up I create a workflow definition. We're using BPMN for that. I come back to that in a minute. Create an executable process. This process has 2 steps, so it's very easy. I start it with a start event. Then there's a so-called service task, which invokes some logic. And the next thing is there's an end event, so I'm done. So that's a very easy, like, start, do something, end, very easy. The cool thing is with that service task, I can attach logic. So the first thing is, what you can see is I use expression language, so I attach a Spring Bean. I show you the Spring Bean in a minute, but that's basically the code we already have, like invoking the REST service. So that hasn't changed at all. But now I have the state machine. So what I can do is I can attach like retry intervals, and that's stateful. That's stored in the database. That can be like lasting for days and even survive like a restart of the system. So in this case, I make it very easy. I say retry 3 times with a delay of period time 1 minute. So that's what I can do there, and that's it. Don't have to do much more here. And then I deploy that flow to the workflow engine, and there it gets versioned and so on and so on. So what's that stripe adapter? That's the last piece of the puzzle. So I have everything in one class. So that's a best practice. No, of course not, but it's very easy to demo. So I have the stripe adapter that's implementing an interface from the engine. And then whenever a workflow instance runs through, we're calling that execute method there. And this is basically what I already had. And this is the code I already had as well. So I still have the REST request. I still do the post. I guard it by history, so that hasn't changed at all. So what you can see is very easy to actually integrate that. And now the behavior changes again. So when I'm calling this and my service, my credit card service is still slow, I can call it. And now what I get back is no longer the history exception, but I get back okay, I said pending, but this one is the more interesting. I get back a 202 accepted. So I'm not sure how familiar you are with the REST return code. So 200 says, okay, everything done, I'm fine, here's the result. 202 accepted says, okay, I got the request, I cannot give you the response right away, but I will come back to you. I got it, I take care. And that's exactly what we want here. So in this case, we cannot call the Stripe service now because it's still slow, history says no, but we want to do it later on. And what happened is that in the background, we basically started a instance of the workflow. So if we go to that one, and all these kind of tools have kind of an operating console. So in our case, that's Cockpit. For the other tools, it might be named differently. And there I can look into the just kicked off instance. So we're having, go to the runtime, we're having one instance basically waiting for that nice little flow. So we do an auto layout so we can show it graphically, and we say, okay, we are in Stripe. We're currently there. We're retrying it. So if I go to the console, you still see the exception, and we are still in the way of retrying. Okay, so far? Okay, cool. The next question, and I come back to that on the slides in a minute, but I want to show you that in the demo right away, actually. The next thing, what normally happens if I show this kind of things is that people say, okay, but now you're having that 202 accepted. And let's assume my Stripe service is going back to normal. So now it's fast again. And if I call it like this, I still get the 202 accepted, right? If I go back to the console, actually, what I can see is that I go to the history. I see that I now directly, immediately executed these requests because it's working. I mean, everything is fine, but I get that 202. And that's very often people say, okay, but now you switch completely to asynchronous processing. We don't want that to happen. And the cool thing is, and I don't go into the details of the code, but everything I show is on GitHub, so you can dive into it yourself. It's actually like a very small piece of code in order to, again, to basically using a semaphore to wait for the workflow instance to complete. And then, and this is version 4, what happens is that I directly get a 202 OK whenever everything is fine. And what you can also see is that this is not slow. Just because I'm using a workflow engine doesn't mean it's slow at all. So it's very fast, actually. And whenever it gets slow here on the credit card, so as soon as we have a failure, we're falling back to 202 accept. And that's actually a very useful behavior very often. Try to do it synchronously if you want to, but fall back to asynchronism if it doesn't work, because that's much better than handing out the error, the failure to your client in order to handle it there. Make sense so far? Okay, awesome. Very good. Cool. So what you can see is that we have a very easy flow. So that's a very easy flow. And a lot of people don't have that use case in mind for workflow engines. They think of very complex workflows. But we currently have a lot of customers doing this kind of very easy flows, actually, just basically to leverage the state machine. Now, that's what it gives you. It gives you the persistent state and a lot of reliability within there. What you also see, and that's actually a very important thought to keep in mind, I come back to that in a minute, whenever the client does that kind of retry, what you have to provide on the service provider side is idempotency. And I think that's, I mean, if you remember two things from the talk, the first probably is the lightweight workflow engines are awesome for certain problems. And the second thing should be do everything you do, provide idempotent services. That's so important in these distributed systems that I should repeat it on every slide. Because, I mean, you retry the stuff, so you probably call that multiple times. You should be really prepared to do that. But that's actually a good idea anyway. I'm using consumer, basically consumer-facing services as another example. Whoever did pay by credit card, probably most of you as well, right? It doesn't happen that often anymore. But like 2 or 3 years ago, it was pretty common. You entered the credit card details, you hit the submit button, and there was something like saying, we are processing your request. Don't hit reload. Do you know that? Remember that? How does that make you feel? I'm traveling a lot. I do these kind of things in the train. That's kind of a really unreliable network. It always raises my heartbeat. Like, oh no, tunnel, make faster, do it faster. And that's really a bad idea. I mean, technically, it should be idempotent. It should be something like, hey, yeah, we're processing your request. Great that you want to pay. You want to order something. That's great. We love it. And we will make sure it will happen. If you hit reload, do it. It's fine for us. I mean, you can take care of these kind of things. And it happens more and more. I mean, these other messages are starting to vanish. And that's the same thing for service-to-service communication. If they want to retry, they should always be safe to do it. Always try to provide that. We have, by the way, another problem to solve as well. And it's great how many stuff you can put in such a simple example. So if you do something like charge the credit card, upstream Stripe service. And then let's say the retries expire. We try it for like 4 or 5 times, doesn't work. Then we could raise something like payment failed, right? Remember, we are distributed systems. And there's really one mean thing in distributed systems, which is you cannot differentiate these 3 situations. So you could call the service via REST. And if you get a network error, it could mean that the request never reached the service. It could also mean the request reached the service, but somehow the service blew up while doing it. Or it could mean that we didn't get the response back because that was lost somewhere. And it doesn't care if you're using synchronous REST communication or sending messages and waiting for response messages. You have that problem all the time. So if you don't get a response back, if you get a network problem, you have no idea if it happened. You cannot. So that's probably a bad idea here, because then you say, okay, I retried it, so I called it multiple times, and then I said payment failed, and probably you have done it. You have charged the credit card. And that's important to also know in these kind of systems. So you have to take care of that. So for example, there are multiple strategies to do that. You could do something like you issue a refund, and probably you say the refund gets an error of no payment there for that refund. It's okay for us. You could ask if the credit card was charged. There are a couple of things, but you have to do it, and again, you have to do it reliably. So your customer is probably not that happy with something like, oh yeah, we wanted to refund, but then we had to restart the server, and sorry, your money, now it's gone. Oh yes, I understood, you restarted the server, that makes sense. Of course not. By the way, what I use here, these nice little diagrams, that's called BPMN. Not sure who of you knows BPMN. That's an ISO standard. That's an important thing here. So it's not in any way proprietary. It's not that yeah, let's say hype at the moment. So a lot of like, if you're looking at what Netflix is doing, also AWS is doing, they are reinventing an own state machine language, like on a JSON format or YAML or whatever. And they're starting where we started with workflow engines like 10 or 15 years ago. So BPMN is really mature. I love the standard, what the language gives you. So I think it's worth to have a look at. But that's probably, again, my opinionated view. But it's an ISO standard, so it's nothing proprietary. And what you saw earlier, what we, for example, provide you also in DSL. So you can program everything in Java, how this flow should look like. And then we create that nice little diagram. Or you do model with a graphical modeler. So that's basically completely up to you. And we are also working on a YAML dialect in order to define these kind of workflows in YAML and then create BPMN out of it. So I actually don't care about this being an XML file where I can understand that some developers are not really like fans of XML. That's, for me, that's okay. But the language underneath, the concepts in there are really powerful. So that's pretty awesome. And the important thing is that we now have that state machine, and that gives us basically time. So that means very often this is referred to as long-running processes, which is kind of a misleading term. I use that myself, but long-running basically means that we wait. So state machines are great at waiting. So that means we're really keeping that state persistent, and we can recover from there. We can go on. We can do that retrying. We have all this notion of time, and that's pretty cool. I give you another example why this improves or basically decreases the complexity in the overall architecture. Let's stick to that payment example. So we let's say we have an order, microservice or service or whatever it is. It wants to retrieve payment, so it calls the payment service. That does the credit card, as we already have seen. And now this time this doesn't fail, but it gives us a business fault, like the card is rejected for whatever reason. So again, the very naive thing, what it could do is just you pass it on to the order service. You pass it on to the order service and say, okay, this card is rejected, we cannot do the payment. And then whenever you introduce new requirements, and you probably know that from GitHub, when GitHub wants to extend your GitHub account and wants to deduct money from the credit card, and if it's expired, they send you an email, please update the credit card. You have 2 weeks. If you do it within 2 weeks, it's fine. Otherwise, we close your account. And this is basically what it could do. You could do something like, oh, it's rejected. We inform the customer to provide us a new credit card. If he does that, everything is fine. And now the question is, where do I want to implement that? Do I implement it in the order? That moves complexity of payment handling to the order. Probably have multiple components doing payments or retrieving payments. And now if I have these requirements, I implement it everywhere. It doesn't make a lot of sense. So it's very often it makes sense to handle it as close to the real requirement or to the service owning that kind of requirement, which in this case would be payment. So it would be much better if payment handles that and then tries to update the customer credit stuff. And whenever this is done or that 2 weeks time off has happened, we send a message like, or give a response like payment received or payment failed. Much better design, because then you have all the failure handling local in the payment. And again, if you're thinking about REST calls, it could be that the order to payment REST call gives a synchronous response directly. Payment happened within like 90% of the cases. Only in cases where this cannot happen, we're switching back to asynchronous. So that's very, that's an important thought actually, if you think of that. And again, in order to do that, and that's why a lot of people don't do it, it's actually you have to support this kind of long-running requirement. Good. And this is how it, for example, it could like in BPMN. Charge the credit card. If that doesn't work, I inform the customer, and then I wait for him to come back, and then I have this notion of time, like 7 days, for example. So that's pretty cool, actually. Another type of failures that could happen always, by the way, is also where we also hand it over to humans normally. It's kind of operating errors. So if charging the credit card doesn't work for kind of Whatever failure it is, not a network failure, but for example, some data conversion failure because Stripe has changed the API or whatever, we get like these red bubble are so-called incidents. So the different tools might use different names, but basically the operating tool can tell you, okay, there were errors while we try to invoke it, like in this case, 317. Please have a look at that. And you get a lot of context. So you see what's currently waiting there, how it get there, what data is attached, these kind of things. And you could then act on that. So an operator could do something, okay, I fix it, or I do a retry, or I skip that. So what a lot of people actually otherwise very often even program in their programs is something like this. I tried to do A didn't work. So I invoke an operator for however I do that, probably log a message. And then this guy says, okay, retry it, okay, abort it, I do it manually, or resume with the next action. We see that all the time. And this is basically built in. So you don't have to model these kind of things, and you don't have to program it. And again, this is a stateful thing, because for an operator, you probably have to wait quite a long time until he gets into the system. The important part, and this is a very important thought actually, is that this kind of workflows are now living within one system. So what I did, it's not the only way. I blogged about that, how you can basically run these kind of workflow engines within services. So what are the architecture options? But what I did here is I used the engine as part of my service. So I used Spring Boot. In this case, I can run the engine embedded as part of the service. So that's a very lightweight way of doing it. So, and this is important because very often people think of workflow engine of being something separate, of like a central workflow engine which I have to talk to, which is not true. It's just a library within the scope of your service, because you want to deal with these kind of long-running system requirements. Sorry. But this is one option. If you're running different architectures in Java, like Tomcat, Wildfly, WebSphere, you can also run it in a kind of similar way. There we run the engine as part of the container, and then you deploy a war file which contains this kind of workflow definition. There are even more ways of doing that, but you can look into the blog post if you're interested. If you're not running Java, which might not be that important here at the moment, but it's important for a lot of customers, you normally talk to the engines remotely via REST, for example. So there are a lot of options to do that. And what I already showed you in the demo earlier on, it doesn't mean that you have to get asynchronous. So you still can have synchronous results. Okay, very cool. By the way, for synchronicity, I discuss it so often. So my favorite story was from a customer, a railway company, and they did order management basically. And that's very easy to understand from a customer perspective. So if you want to order a ticket, basically, you go on the website, you search the connection, you hit the button, you say, okay, I want to have a ticket. Yes, I want to have a reservation. You select the seat, and so on, and so on. And at the end, you click on book, and then it does the payment, it does the seat reservation, a couple of other things, generates the PDF, and presents it in the browser, right? So that's what normally happens. And they are so convinced that this must be a synchronous thing. The customer wants the PDF right away shown on his screen, which I think, no, why? I mean, I don't want to have a PDF anyway. I want to have it in the app. And if the choice is between, okay, I normally get a synchronous response, but if they blow up, and that happens, for example, if you get a new credit card, it happens for me for all the sites, like they say, I cannot process the payment. Ah, yeah, right, I have to provide new credit card details. Oh no, all my details are gone. I have to redo the whole process. That doesn't make any sense. That's not nice for the customer. So I don't think synchronous response are so important like all the people always think of. And I actually like that quote very much. It's from Todd Montgomery and Martin Thompson from the GoTo in Chicago, quite a while ago, but it's still true. So they said synchronous communication is the crystal meth of distributed programming. So it's like, I mean, we are so used to do synchronous stuff, calling a method, calling a REST service. It's so easy to understand. I just call it, get a response back, that's it. That we somehow know, okay, that might not be the right way, because what I said earlier with the REST request, I even have no idea if it reached the other party if I get an error. So it's not really synchronous as we think of it like a method call. But we think of it like a method call, and it's so easy, and let's do it again just one time, and then next time I do it better. So it's sometimes make very much sense to question these kind of synchronous patterns. But if you look at asynchronicity, That's very interesting as well. So if we make the same example like I had earlier on with the check-in, the barcode generate, it doesn't change that much because now this time we're using messages sent back and forth because we probably even still use request response. And okay, now we have to monitor timeouts, but we basically do the same thing. We want to have it local. We have the notion of time. So again, a workflow engine might be very beneficial to do that. So we could do something like send the generate barcode command, and then I wait for it. And if this doesn't happen within a certain time frame, I might even resend that. So this is like I do it every hour. I resend. That's my retry. Do that if I like to. And you even again, it's stateful, so it's very reliable and very easy to handle these kind of times. And we could even do more sophisticated patterns. This is probably, if you don't know BPMN, it's probably a lot in one slide. But I think it's very easy to catch. So this one here means it doesn't matter where I am currently in that workflow here. Whenever it's 4 hours before the flight starts, I cancel whatever I do there and do something else. Okay? The business requirement here might be a bit, probably not what they want to do, but whatever. So they get the idea, I hope. So for me, that's not even such a big difference here if I'm doing synchronous or asynchronous. It has to be, again, you have to retry. It has to be idempotent on the other side, so that doesn't change that much, actually. Who uses a message bus here in his architecture? Oh, not many people. Not many people. Normally it's more. Okay, so Vienna has to do some more messaging. Who has, from the, I think 3 people, who has no problems operating that message bus? Oh yeah, 1. Oh, very good. Want to talk to you later. No, normally it's like, but it's really cool because normally it's like one guy showing up, okay? I don't have problems. Normally, people have a lot of problems with this kind of messaging architecture. Why? Because they end up with like sending messages there. They couldn't be delivered, so I have dead messages, for example. Whenever I have these kind of dead messages, I even saw customers having overflowing dead message queues, so they lost messages. Whenever they look at the message, they have no idea where they're coming from. They can sometimes not even access the payload or even fix the payload because they see problems in the data. They cannot easily like click a button and say redeliver all these kind of things. So they build a lot of tooling, and this is normally called something like Message Hospital. Even Sam Newman in the microservice book, he also named that Message Hospital. So that's quite a common thing to do. It's amazing in 2018 that you still have to do that, but I think a lot of people do that. And that's interesting. And what I see a lot of customers currently doing, or at least some of them, is that instead of what the normal pattern is, what we see with our workflow engines is like we're having that workflow and this is actively calling another service via REST or actively sending a message into a queue to another service. Customers start to do changing the direction of the communication. So this is kind of, the other one was kind of a push thing. Now it's a pull. So the service could ask for work. So we have an API for that. I'll show you that in a minute. And this allows to build architectures where we use the workflow engine as kind of a work distribution. That's a very interesting thing, actually. And then saying, okay, this service, like the service A, is still owning the workflow model and deploying it to the engine, but other services can fetch work, and then it works like a kind of a queue, which I don't want to propose as this is the architecture how you should use it. I know a lot of discussions about smart middleware, which you should avoid, so I'm definitely with that. But I know that a lot of customers actually doing that quite successfully. So that's for also interesting option to have in mind. I show you that in the demo in a minute. I have to actually look on the time. So last thing I want to talk about, and that's actually my very, very favorite topic, and to do a proper blog post on that for ages, distributed transactions. So we have this distributed system. Who uses two-phase commit XA transactions in production? Oh, 2 people. You're happy with that? I cannot see your face, actually. You have to raise the hand. You're happy? No? No? Oh, no. I can even see that in the dark. It was like a very, very clear sign of not liking it. There's actually good literature on that. So you probably know this. There's from Pat Helland, he was at Amazon at that time. He wrote a couple of good papers. One of them is Life Beyond Distributed Transactions and Apostate's Opinion. So he basically explains very well why two-phase commit distributed transactions in a technical way don't scale beyond a certain limit. So if you have like a scalable system, it doesn't matter, it doesn't work. And I even see a lot of other issues with distributed systems. So my favorite story is a question on, how's it again, Stack Overflow. And somebody asked something like, whenever I start up that JBoss application server, I get a warning from that Arduino transaction manager, whatever that is, for something like this. It looks like that. And then another guy answers and says, okay, you have to go to this directory and delete all the files. And the guy answers or comments on that and says, oh yeah, awesome, that worked. Yeah, he deleted the pending aborted transactions from the transaction manager. He would have to take care of them himself. So these are like documented inconsistencies of his transaction manager. Because sometimes the transaction manager cannot, he cannot do magic. If it doesn't work in the end, you have to sort it out. Nobody understands these kind of things. So it's a very bad idea actually to go into these kind of distributed transactions. But you will have the requirement of like doing like 3 things in an all or nothing semantics. Like you do all of them, and the third thing fails, you want to roll back basically the other thing. And what you do in these kind of distributed systems, and you probably find something also under the name Saga pattern that starts to get a more common term nowadays. And in BPMN, that's called compensation. And this is how it looks. So you could do something like, I want to charge the credit card, but before that, I probably deduct money from the customer account because he probably has a voucher or whatever. And if the credit card handling fails now, we can do an undo, basically. That's the compensation there. So there we trigger it. And that means all the activities which were executed successfully in the past and have this compensation activity configured, there the compensation activity is executed. And that means a semantically undo, right? So you probably see it on your on the credit on the customer credit account, for example. You see, okay, this was deducted and then it was refunded. So it's not like a real cancel of a transaction, but it basically makes sure that in the end everything is consistent. And again, this is totally reliable. So even if you raise that payment failed here and the customer credit service is not available at that moment, you just retry. You make sure it will happen at the very end. Important. And that's kind of a true nature of a distributed system. You can live with these kind of temporarily inconsistent state where you say, okay, I've deducted credit but not charged, so that's kind of inconsistency. But you live with it. You can live with it as soon as it's sorted out in the very end. Let's quickly go into that one, the last demo of the day. So what I have is actually, I have what's on the slide. So what I said earlier, you can also use, oh no, that was the wrong one. You can also use the, thanks Eclipse here. Hello? Why? Oh, that was Java class, sorry. Yes, thank you, Eclipse. So you could also use the modeler. That's what I meant earlier. That's a graphical modeler. And this is exactly what we had on the slide. And if I run that, which is version 6, you can see that this is happening. What you can also see, just make sure that my credit card service is back to normal. Because then I start to get also, oh no, I get 202 accepted all the time. Why? That's important. I wanted to quickly show that. Because I have this deduct customer credit, and this time I do what I meant earlier. I use that as a work distribution, so I don't actively call the service here, but I let some worker asking for work. And to make a bit more fun here, I used actually JavaScript. It could be everything. It's in GitHub again. You can look to the code. It's not that interesting here, but the basic idea is I now ask the REST endpoint of the engine to fetch for work and hand in a couple of parameters, which are not that important at the moment. And then what I can do, I can start that. Yes. Okay, and it starts to processing these instances. So the ones I already started are now processed. So that's kind of the asynchronous stuff because I brought it back. And now I start to get 200. Yeah, that's actually what I wanted. So some of them fail. That's kind of a random thing. I'll show you that in a minute because I want to roll back that transaction. Some of them fail, but most of them should be at 200 okay. So let's do a couple of them. And what you can see then is if I go back to the monitoring part, what you can see for the payment beat 6. If I look to the history or into the history, you can see that I now had like 7 instances which completed completely, 5 of them failed, and for these 5 of them, I also did the restoring. We could look into the sys out of the thing, but I think you believe me. And you get a lot of like these kind of audit data, historical stuff, and so on and so on. So that's pretty awesome. Okay, so that's the next part. So if you want to do this kind of compensation thing, it means that the service provider has to provide it actually. That's the next tricky part of the distributed system. Very often you can do something like retrieve money, but refund it, it's probably not there. So plan for that from the very beginning. And then you have a lot of basically power to handle these kind of problems you have there. You have to handle state a bit, but that's actually very easy if you use the right tools for that. And then if you look at that, I use one random example from a client, 24-hour fitness. They're doing gyms in the US. You know what a gym is doing, probably. Always ask for it. No, they're doing a lot of things there, like 20 million stuff. And they said what most of the people using that are saying, before mapping processes explicitly with BPM, the truth was buried in the code and nobody knew what's going on. So that's the other side of the equation. So as soon as we have these kind of workflows, they're visual, you can see what's going on. It's always the truth. It's not something you program somewhere else. So it's really living documentation for this kind of long-running stuff. You have the operations part, that's what I showed. And if you like, by the way, if you're more, I showed a lot of things about request, response, REST, and even like messaging, request, response. If you're more into DDD, event-driven stuff, there's also an example. It's online. We don't go into details today. It's using Kafka underneath and 2 Camunda instances there, Spring Boot again. I showed that last year here as well. If you're interested in that, ask me later. There you can see what I meant earlier with the workflow now really lives within a service. So we have different workflows for different services, and we don't have any central workflow engine. That's not necessary at all. Awesome. If you ask for people really doing that, there are a lot of people really doing that. One example I personally like, Zalando, they're also active here, so they're shipping clothes. They're pretty big, and they showed how they do their order fulfillment process. So the process of Zalando, they're using Kafka underneath, they're using Camunda, so it's pretty comparable to what I showed here, and they're doing it more or less exactly like that. So that's pretty awesome. So that's it. That's a summary. So a lot of people know about fail fast, which is great. I think that's better than like 2 or 3 years ago, but it's not enough. For a lot of use cases, not for all of them, but for a lot of use cases, you can do better by introducing long-running things. And I mean, this introduces new components like the workflow engine, but it gives you a lot of concepts to handle failures much more local, and that basically improves a lot of things in your architecture. So that's it. That's all I have. What I said earlier on, I'm still around for the next like 2.5 hours. So if there's anything, let me know. I cannot join tomorrow. I cannot join in the evening. I'm sorry. But thanks for coming. Have a nice day.